Buenas tardes, mis estudiantes, y bienvenidos a CSE1PES y CSE5CES Numeric Bases. So, this is a math-heavy lecture. I apologize for that for those of you who don't really like math, but hopefully it's not as intimidating as it could be. I'll try to help you through it. But so today we're going to talk about, we've talked a little bit about binary, about octal, hexadecimal, decimal. This lecture is going to say, what do we mean? Why do we care? How do we use this information? So in mathematics, base is used to mean the number of symbols that a counting system uses to represent numbers. And in theory, you can use any number bigger than 1 as a base for your counting system. A base 1 counting system is not very useful because you can only count to 0. Not that great. In practice, the counting system that we're most comfortable with by far, really the only one that you see out in the real world, is decimal, which is also referred to as base 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10. Base 10, we've got 10 fingers, 10 toes, most of us. That's how we learn to count. There are 10 symbols in decimal counting. The 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 characters. But in computing, there are very good reasons to use counting systems other than decimal. Decimal is great. It's what humans are used to, but it's not what computers are good at. The main reason is that, in fact, most computers are only capable of understanding 2 symbols. And that's because their memory is made up of transistors. If you go all the way back to lecture 1, we talked about how modern computers you can think of as millions or billions of little switches that can represent either on or off, and that's it. So they don't have 10 fingers and 10 toes. They have 1s and 0s. So if you really want to understand what a computer is doing, you need to be able to understand, at least on some level, binary, which is also called base 2, because there are only 2 symbols, 0 and 1. But binary is a real pain to work with directly. So other counting systems, other bases that computer programmers tend to use are octal, which is base 8, where the symbols are 0, 1, 2, 3, 4, 5, 6, and 7. And hexadecimal, or base 16, where the symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So octal has 8 symbols. 8 is also 2 to the 3rd power. Hexadecimal has 16 symbols, which is 2 to the 4th power. So this is really convenient, as you're going to see as we move on. So 1 byte, which is 8 bits, can be represented with 2 decimal digits, or 2 hexadecimal digits, I'm sorry. Each hexadecimal digit consists of 4 bits. 2 hexadecimal digits equals 8 bits. So you can represent a byte of memory with 2 characters, and that's actually pretty common. And if you're a really low-level systems programmer, you're going to want to get comfortable with hexadecimal. So in the printf lecture, we saw that C provides conversion specifications for octal and hexadecimal. It does not provide one for binary, surprisingly enough, but there are other operations in C, such as the bitwise operators that we just talked about, that work directly on the binary representation of data. So as far as C is concerned, there are 4 special bases: decimal, or base 10, binary, or base 2, octal, or base 8, and hexadecimal, or base 16. So it's pretty straightforward to convert other bases into decimal. So if you have a number in some base, let's say base n, that is written out as symbols k, k minus 1, down to 1 and 0, where each S denotes a single symbol. Also note that I numbered these symbols starting from 0, not from 1, so it's 0 to k, not 1 to k, or 1 to k plus 1. This is very common practice in computing, so I suggest you start getting used to it now. When you're counting, start counting with 0, because binary is 2, 0 and 1. So 4 is, if you have 4 elements, they're probably going to be numbered 0, 1, 2, 3. That's just the way it works in computing most of the time, so I'd encourage you to start getting used to it now. So I've written some mathematical formulas here. I will show you some examples of these formulas on the coming slides, so you don't necessarily need to be shocked by the symbolism. So to get the equivalent value in decimal, you compute symbol 0, the rightmost symbol, times n to the 0, which is 1, plus symbol 1 times n to the 1, plus symbol 2 times n to the 2, plus symbol k minus 1 times n to the k minus 1, plus symbol k times n to the k. If you're more mathematically inclined, you can write it out with a summation notation, where you're doing the sum from 0 to k of symbol I times n to the I. So let's look at some examples of this. So we've got a binary number, 101, that we want to convert to decimal. So we do 1 times 2 to the 0, plus 0, which is the middle symbol, the second symbol, which is also symbol 1, since we started counting at 0, times 2 to the 1, plus 1 times 2 to the 2. So that's 1 times 1 plus 0 times 2 plus 1 times 4, which is 1 plus 0 plus 4, which is 5. So 5 in decimal is 101 in binary. We can also do the same thing for a more complicated binary number, for a whole byte. So 8 bits, 11001010. And again, we can do exactly the same thing. It's 0 times 2 to the 0, plus 1 times 2 to the 1, plus 0 times 2 to the 2, plus 1 times 2 to the 3, plus 0 times 2 to the 4, plus 0 times 2 to the 5, plus 1 times 2 to the 6, plus 1 times 2 to the 7th. Which turns into 0 times 1, plus 1 times 2, plus 0 times 4, plus 1 times 8, plus 0 times 16, plus 0 times 32, plus 1 times 64, plus 1 times 128. In other words, that's 128 plus 64 plus 8 plus 2 equals 202. Okay? And that's just a specific example of this formula where n is 2. Okay? We can also convert octal to decimal, surprisingly enough. So the octal number 555 is 5 times 8 to the 0, plus 5 times 8 to the 1, plus 5 times 8 to the 2, which is 5 times 1 plus 5 times 8 plus 5 times 64, which is 320 plus 40 plus 5, which is 365. We also have the octal number 12345, which we can do the exact same with. 5 times 8 to the 0, plus 4 times 8 to the 1, plus 3 times 8 to the 2, plus 2 times 8 to the 3, plus 1 times 8 to the 4, which turns into 5 times 1, plus 4 times 8, plus 3 times 64, plus 2 times 256, plus 1 times 2048. Add this all up, you get 2,789. And again, we use the same formula we did before, where the symbols are the values 0 through 7, and n is 8. Okay? You can also do hexadecimal. So 7e is, I'm sorry, this should be an e, not a c. That's my fault. We have e times 16 to the 0, plus 7 times 16 to the 1. That's 14 times 1 plus 7 times 16. 112 plus 14 equals 126. You can also have the hexadecimal value ACDC, a little akadaka. We have C times 16 to the 0, D times 16 to the 1, C times 16 to the 2, A times 16 to the 3. That's 12 times 1, plus 13 times 16, plus 12 times 256, plus 10 times 4,096. That's 40,960, plus 3,072, plus 208, plus 12, is 44,252. Again, exactly the same formula. N is 16. The symbols are 0 through F, which corresponds to the numbers 1 to 15. Okay? So converting from anything else to decimal is pretty easy. It's always going to be this formula. Whatever your base is, whether it's base 2, base 8, base 16, base 43, base 97, you can use exactly the same formula. To convert between binary, octal, and hexadecimal is pretty straightforward. They're all based on powers of 2, which enables some shortcuts. It's actually quite easy. So to convert binary to octal, just take 3 digits of binary at a time. So 101 in binary is 5. 110 in binary is 6. So the number 101, 110 in binary is 101, 5, 110, 6, 56 in octal. We can check that math. So converting from octal to decimal, 56 to 46. And there you go. We're good. So binary, you get 46. Octal, you get 46. If you need to, you add zeros at the beginning to make a set of 3 bits to make your life a little bit easier. So we have 1010101, which is 7 bits. If we want to convert that to octal, we want to have a multiple of 3, so we make it 9 bits by adding 2 zeros at the beginning. So we have 001 in binary is 1, 010 in binary is 2, 101 in binary is 5. So 1010101 in binary corresponds to 125, 125 in octal. Similarly, 100101010 in binary. We add 2 zeros to make it 12 bits, a multiple of 3, and then that's 001, 001, 001, 010, which is 1112. So 10010001010 in binary is 1112 in octal. Okay? Binary to octal, pretty straightforward. Just group them into groups of 3 and take the result, and that's your octal digit. Converting binary to hexadecimal is just like that. It's even easier, only now we're considering 4 bits at a time instead of 3 bits at a time. So if we have 8 bits, 1010, 1100, we can convert that to binary, to hexadecimal, by taking the first 4 digits as a chunk, 1010, which is 10, which corresponds to A, and 1100 is 12, which corresponds to C. So 1010, 1100 in binary is AC in hexadecimal. You can follow the check here, converting directly from binary to decimal, we get 172. Converting from AC in hexadecimal to decimal, we also get 172. Mission accomplished. Okay? We can look at some more examples. Again, if you need to, add zeros at the beginning to make it a set of 4 if you need to. So 11011 is the same value as 0011011. Take these binary values to hexadecimal. So 0001 is 1. 1011 is 11, which is B. So 11011 in binary is 1B in hexadecimal. Here we have 2 bytes, 16 bits. They're already in chunks of 4, so we just take them in chunks of 4. 1001 is 10. No, 1001 is, I did that math wrong. 1011 is in fact A. 1001 is 9. 0111 is 7. 0011 is 3. 0101 is 5. 1011, 0111, 00110101 is A735. 10010111, etc. should actually be 9735. Okay. Octal to binary is also easy. Just convert each octal digit to a set of 3 bits. So we have 7 in binary is 111, 3 in binary is 011. So 73 in octal is 111011. It checks out. Hexadecimal to binary, also easy. Just convert each hex digit to a set of 4 bits. F is 15 is 1111. 5 in binary is 0101. So F5 in hexadecimal is 11110101. They both are 245 in decimal. Okay? So converting from anything to decimal is pretty straightforward. Use the formula, the summation from 0 to k of s sub I times n to the I. Converting between the binary, the power of 2 representations, is pretty simple. Binary to octal, take groups of 3. Binary to hexadecimal, take groups of 4. Octal to binary, turn it into groups of 3. Hexadecimal to binary, turn it into groups of 4. But converting from decimal to other things is not that easy. It's a little bit more complicated. But luckily, there is an algorithm, a step-by-step method of solving a problem, to convert from decimal to other bases. So let's check it out. So if x is your number and b is your base, x mod b modulo, which we talked about in the arithmetic lecture, the remainder when you integer divide x by b, is the last digit of x's base b representation. Now integer divide x by b to remove its last digit. Repeat this procedure to yield the digits of x from least significant to most. Okay? And that's how you do it. So let's look at, let x be a number. Okay? X is 42. Then if b is any base, okay, let's see, b is 8. So we're computing the value of 42 in octal. We take x mod b to get the last digit of the octal representation. So 42 mod 8 is 2. 2 is the remainder when 42 is integer divided by 8. Now you integer divide x by b to get rid of the last digit, to get rid of that 2, and that's 5. Repeat in this procedure yields the digits of x from least significant to most. So from the last slide, the new value of x is 5. Then if b is any base, which is still 8, x mod b is the last digit of x's base b representation. So 5 mod 8 is 5. 5 is the remainder, my mistake, when 5 is integer divided by 8. Now integer divide x by b to remove its last digit. 5 divided by 8 is 0, so we're done. If it wasn't 0, we could begin again with the result as the new value of x. So 42 in decimal is 52 in octal. You can follow the same procedure, the exact same procedure, to convert from base 10 to any base. Not just binary, octal, and hexadecimal, but base 3, base 11, base 1329, base 27,426, whatever you're interested in. And note that since C gives you modulus and integer divide operators, it is pretty easy to convert this algorithm into a C program. But you do need to know about how to do repeated tasks in C. So that's going to be next week. After we talk about loops, you'll know everything you need to know if you wanted to make a program to do this. Okay? So to recap, there are 4 numeric bases you need to be comfortable with as a programmer. Decimal, aka the normal numbers. Binary, or zeros and ones. Octal, or base 8. And hexadecimal, or base 16. Now we know how to convert between any of them. A little bit of practice and you'll get very comfortable very quick with the base 2 representations. And I close with a joke. Why is it that programmers always confuse Halloween with Christmas? Because 31 oct equals 25 dec. All right. Thanks very much. Be well. See you next time.